I just want to introduce our presenter, give you a little bit of a brief background on the topic, and then I'll let Captain Shepard come in and talk. The topic of tonight's meeting is the shipboard environment aboard the International Space Station, and we're very, very pleased to have Captain Bill Shepard, Navy captain, retired, and NASA astronaut. Well, we've tried to make it a brief bio for you, but he has so many accomplishments, it's hard to make it brief. Captain Shepard received a bachelor's degree in aerospace engineering from the Naval Academy and master's in engineering degrees in mechanical and ocean engineering from MIT. Captain Shepard started his career in 1971 as an underwater demolition frogman and Navy SEAL, and in 1984 he was one of 17 astronaut candidates in NASA's Astronaut Group 10. Captain Shepard flew as a NASA mission specialist and flight engineer on 3 space shuttle flights, STS-27 Atlantis in 1988, STS-41 Discovery in 1990, and STS-52 Columbia in 1992. Captain Shepard and his crews carried DoD and scientific payloads to space, performed materials and life science experiments in microgravity, and launched the interplanetary probe Ulysses into the first polar orbit of the Sun. In 1993, Captain Shepard was selected to serve as program manager for what was then the new International Space Station. It was a 16-nation partnership to design and build this new orbital gateway to space. In 1996, he was named to command the first expedition, Expedition 1, to the new station, and in 2000, Captain Shepard's crew, himself, and Russian cosmonauts Yuri Gidzenko and Sergei Krikalev launched from Kazakhstan aboard the Soyuz rocket, flew into Earth orbit, and docked with the space station. From October 2000 until March 2001, the Expedition 1 crew brought the space station to life, establishing the operational and research capabilities of the new outpost. The 4.5-month mission covered 58 million miles, which is equal to 2/3 the distance between the Earth and Mars. Captain Shepard left NASA in 2001 to serve as a technical advisor to the Navy SEAL headquarters in California, and later was the U.S. Special Operations Command's first science advisor in Tampa, Florida. Captain Shepard is currently a private consultant to government and industry, helping to advance national security capabilities and technologies. The topic itself, tonight's presentation is going to introduce NASA's efforts to design, build, launch, and operate an integrated orbital space platform in collaboration with 15 other countries, including the Russian Federation. Through slides, video, and a narrative description, this presentation describes the early construction, launch, and crew operations of the first expedition aboard the space station. And the space station now serves in part as a prototype for future large expeditionary vehicles, ones which will take humans to live and work far beyond Earth orbit. A space station is a shipboard environment, distinct from an aircraft experience, and the presentation will touch on the many parallels with ship design, engineering, and operations, as well as themes of technology, history, design, cross-cultural understanding, teamwork, risk, and performance. The talk will conclude with the presenter's focus for our vision for our future space explorations, and a discussion about the vehicles and program activities which will be required to make them happen. As I mentioned earlier, the presentation is accredited for 1 PDH. Please, if you want to take advantage of that, please hand in your forms to Alan Rowan after the meeting. We do have blank forms up here. And with that, Captain Shepard.
Thank you, Brad. And where's Raju tonight? Where's he? Oh, yeah. Raju from Stevens is to blame. He kind of roped me into this. But it's really great to see so many, particularly young faces here. And it makes me think back to what is now more than 45 years ago. I was in some of the seats that you guys are in as a young student. I grew up, my dad was a Navy pilot. We were living in Long Island. He was in aerospace. The company that he worked with had done a lot of the life support, including the spacesuits, on the early Mercury and Gemini flights. So conversations about space and astronauts and the spaceflight program were very current in our household back in the early 60s. So I grew up thinking, boy, that was really cool, and the way to do that would be to do something with aviation. So I went to the Naval Academy and studied aeronautical engineering. Unfortunately, right before I graduated, I had a small problem with a little thing called the eye chart. So I went to the SEAL community and did that for about 13 years. In the middle of that, I was in MIT in the 70s with Professor Ray Matheson back there. He and I were classmates in a long-standing program that the Navy has had in cooperation with MIT when the Navy used to design ships, and they were pretty good ships at that. Great experience to a highly technical education. I met a lot of great professors, and I always saw, I came away from MIT with notebooks full of stuff that maybe I didn't understand at the time, but I decided that I would try and stay focused throughout my career to fill in the gaps and get my head around the things that were still academically kind of opaque to me. So we're going to have a presentation. I'm going to show you a video, and I'd like to have some really aggressive questions when I'm done. Particularly from the young folks, because I want to hear what you guys think about the space program, where it's going, and your thoughts on what you want to do in your future. When I got to NASA, I flew 3 shuttle flights as a flight engineer and someone trained to operate the robotic arms. And as a flight engineer, you sit in the middle of the flight deck and you manage several of the key systems, particularly the main computers, and you kind of keep an eye on the pilots up front. Their job is to fly the vehicle principally on landing and doing all the on-orbit piloting. And things can go downhill in a hurry, and somebody's got to keep track of the configuration of the electrical power systems, the hydraulics, the thermal, the life support, fuel cells, a lot of different things, and that's the flight engineer's job. So I enjoyed doing that. In the middle 90s, I was asked if I would join a team to attempt to reconfigure the space station program, which at the time was called Freedom. President Reagan started it in 1986, and so I got parachuted in with a number of other NASA people and astronauts to try and redo the program. This was 1993. The Clinton administration was in town. NASA had done 6 major redesigns of the space station. They were on their way to do a 7th, and it had been going for 6.5 years. They had spent $11 billion, and NASA had, and its contractors had not produced a single pound of flight hardware. It wasn't a very good record, and so the decision was made from the White House. NASA, see if you can fix the space station, and oh, by the way, go to Moscow and bring aboard the Russian efforts to fly their 2nd generation spacecraft called the Mir-2 and make that part of the international program. So we worked on that from 92 till basically 1998, when the first element of the space station went into orbit. Our flight started in 2000, and I'll show you some of the highlights of that shortly. But today the station is up in orbit. We have 6 astronauts and cosmonauts aboard. We've had 55 over the last 17 years. We have not had a minute, not an instant, where a human has not been traveling out in space doing something. And as a program, it's extremely large. It has to be one of the largest technical endeavors that this country has ever been involved in, certainly outside of wartime. And I think today it's really a model for how countries need to work together to do things which will be more expansive in space, and we'll touch on that shortly. In my role in the space station program, as it was cranking up, we had a chance to do a lot of integration and the latitude to do redesign was somewhat limited, but I tried to impart as much as I could from my experience as a Navy guy and a shipboard background, because I was pretty sure that the culture that NASA had, which was generally flying short missions, was too much like the way we design, build, and fly airplanes. And these large space vehicles had to be different. So I'm going to talk about why I think space stations are ships. You got to go back fairly early. One of the things I like to do is kind of do my homework. Where did this stuff all come from? This is a large subsonic wind tunnel. It's in the Navy Yard in Washington, D.C. This was in the middle of the construction in 1913. It had an 8-foot square test section. This was the largest, when it was finished, it was the largest wind tunnel in the world. And once they had it running, it ran 16 hours a day, starting about 1916 for 3 years. I mean, it was very heavily used. And it's kind of the granddaddy of aeronautics, but it was designed and put together by naval architects. So early on, people, the Wright brothers were very studious. They had a lot of academic, scientific approach to their design. Others were not. Glenn Curtis in particular, they jumped in something that they put together and it worked because it worked, but they really didn't understand why. Then it was the hydrodynamicists, the naval architects, who kind of dug them out of the hole, particularly in terms of drag and fluids, because the aeronautic domain had not been developed, and they got that all from naval architecture. And pressing on through the war years and post-war, most of the rocket things that were put together had some legacy from what at that time was airplane technology, particularly the wind tunnel testing, the controls and dynamics from aircraft, instrumentation controls, and a lot of the subsystems like tanks, pumps, valves, fluids, things like that. October 1957, about half the room was probably alive when that happened, the other half was not. For the folks that were not on the planet yet, this was a tremendous culture shock to this country. And I still remember that. I was 7 years old when that happened. And the Congress, the administration, the country was upside down that we were going to lose the space race because the Russians were ahead of us. And what the hell happened? And it really changed the direction of education as well as our national interest in having a strong space program. And I think in a way that's what it took to put men in space and also to have a program like Apollo that went to the moon. But if you really want a good background on all this, I commend to you Tom Wolfe's book, which is also the movie The Right Stuff. The astronauts were test pilots because that's what President Eisenhower said at the time. He wanted test pilots. And these folks came to the party wanting to have a control stick and a throttle, and by gosh, they were going to make these things into airplanes. The shuttle was essentially an airplane that could launch like a rocket and land like a large transport. And the way it was built, the way it was operated, the things about it were very airplane-like. And unfortunately, our last shuttle got grounded 6.5 years ago. But just there one point that I wanted to make that might be of interest to the naval architects here. Some will recognize this. It's a World War II destroyer, kind of our standard get-it-done ship, probably one of the technologies that won the war in the Pacific. And this was a vessel that weighed 2,000 tons standard displacement. And I'm pretty sure these are long tons. I didn't read that in the Wikipedia page. But anyway, this is the last flight of, I think this is Atlantis. This is 2011. This is one of the last 2 shuttles to fly in space. This stack, the space shuttle, the 2 boosters on the side, the orange fuel tank. This has a mass that's equivalent to that World War II destroyer. Equivalent to a destroyer. It's sitting on its tail. They're going to light the boosters, crank up the main engines. That thing's going to go straight up, and it's going to be in a vertical climb going supersonic in 40 seconds. Just to give you an idea of kind of what's involved here. And I tell my friends, I said, anyone that can look at a shuttle launch, even from a distance or on TV, and be blasé about what they're looking at, I say to them, you don't understand what's happening. So, a lot of moving parts, a lot of energy. ISS. The design really started in the mid-1990s. And as I said, we were bringing together a system that had two segments, one that the U.S. managed and one that the Russian Space Agency was responsible for. But we were able to bring a fair amount of naval terminology and even some technology into the space station. ISS, as we call it now, it has a port and a starboard. It has a deck and an overhead. People go through hatches. We have bulkheads. The structure has flanges. When we talk about drawings, we talk about water lines. If we don't like the way something looks, we say it's not fair. And these are all artifacts from the naval architecture tradition. But even beyond the words that we use to describe it, a ship, for the most part, is a platform that's designed to be a long way from home base, to be relatively self-sufficient, and capable of invoking lots of different ways to get the job done. This is not how airplanes are designed now. You have your 737 or whatever flying across the country. The data is going down to a control center in the middle of the heartland somewhere. You have technicians looking at data and they say, okay, when flight 1282 gets to Houston, you need to pull that tire because it's losing pressure, or the APU is bad, or whatever. So it's a maintenance concept that's very much based on analytics and fixing it when you get home. A spaceship can't have that luxury. So we did a lot of our thinking about ways to orient the craft, to know where it was, to control the electric power, to manage the life support, the computing. All that had a lot of redundancy built into it because this is what you would need on a ship, and we thought it was a good idea to put it here. We also had some issues. We have a lifeboat on the station on a bad day. The crew can bail out. They can get in a Russian Soyuz capsule. They can be on the ground in a little less than 2 hours in a real emergency. And we thought that was an essential capability. But one of the things we have to think about is, in the future, we're going to have large vehicles that go to the moon for sure, and maybe on to Mars beyond that. And if you're on a spaceship going to Mars, and you want to jump in your lifeboat, where are you going to go? And this is a big thing that we got to get used to. The whole strategy of how we will do these long expeditions has got to change. And I don't mean to be too trite about the Nina, the Pinta, and the Santa Maria, but we will see groups of ships in situations like that, because we probably do not want to rely on the robustness of a single platform. A lot of other things that we talked about, how we would organize the coordinate system on the shuttle or the space station. The shuttle uses the center of gravity for the stack, and they use X forward, Y out the right wing, and Z down. I think ship dynamics, that's where they go to. The station did the same thing, although our center for the coordinate axis was the main truss axis. But when you're flying in space, you have very different reference frames that you've got to be used to. One is a vehicle-centered frame, vehicle going forward. This is the starboard side, and this is down. But you've also got Earth reference, and you've got inertial reference. Sometimes you want to keep the station pointed so that inertially as it orbits, it's not changing its orientation, and your aspect to the Earth is rotating because you're going around the Earth, but your inertial reference can be fixed. Operations, a lot of transfer from shipboard routine. We call it launch, docking, undocking, berthing, drifting. We use these words, and I talked a little bit about the culture in which we operate. I found it was very surprising when I got to NASA. Crews fly on the shuttle when the shuttle was up. They have about a 16-hour workday. They go to sleep, and the shuttle shuts down for 8 hours. And this was completely foreign to me because I'm going like, who's got the anchor watch? You know? But they have such instrumentation, that NASA's sense is that they can monitor things well enough on the ground that they don't have to worry about that. That works until you get in a situation where your comm delay is extensive. And once you get past the moon, you're going to have significant delays in your comm link. It could be 20, 30 minutes between sending a signal out, having it processed, getting an answer, and seeing what the response is. Right now, when we do stuff, if you hit your control on your digital TV, if you have a lag of 100 milliseconds, you're not happy. And we're used to that control environment. This is not going to be the way things go down in the future in space. We talked about onboard repair and replace, and just in general, I tried to do my best when we were flying our first expedition on space station to bring as much as I thought was reasonable for the nautical and naval culture to what was going on. The Russians were looking at me like, well, this guy's really weird, but I think now they really like it. So here's what the station looks like today. You can go on a website. NASA has a program. You can tell NASA where you are in the country. It'll show you the times and locations where you can go outside and see the station go by. This is the third brightest object in the sky behind the sun and the moon. It's very visible. I often wonder exactly what material NASA and our partnership used to coat the outside of the space station, because people that I ask about space station, they don't know anything about it. I'm going like, this is the greatest stealth program we've ever built, because nobody knows it's even up there. So I commend to you to take a look some night, and you'll see it. It looks like an airplane, and it's moving fairly fast. It'll go from one end of the horizon to the other in about 6 minutes. So now, okay, back in. This is the largest swimming pool in the country. It's in NASA. It's where we do our zero gravity training with spacesuits that are weighted down, so we take all the moments. We have our buoyancy matched to our weight. And we try and be simulating weightlessness as best we can. Here you can see when I learned the secret Moscow training base, where Yuri and Gagarin got ready for his first flight. You can hear Yuri and I talking in Russian. All of our conversation, the first part of our flight was all in Russian. Sergei jumping out of a Soyuz capsule. This is a kind of a boilerplate capsule. We're in the Black Sea, and we're practicing having ships and aircraft find us after emergency landing and pick us up. And I'm doing some signaling there. Same type of training in the winter. Here we are in a forest outside of Moscow, again practicing signaling, making a little camp, and then waiting for Ratchet to come get us. I did a lot of professional camping as a Navy SEAL. I really like this part of the training. This is 1998, the first piece of space station called Zarya, which means sunrise. It comes out on a very large booster. This is in Kazakhstan. And the Russians are going to launch this. It's going to go about 190 miles. And the modules that are going to be carried out later, and this is the first start of the assembly. Space Shuttle Atlantis with the U.S. module docking to Zarya right here. And this is kind of the guts of how modules are put together to form the station. Sergey had a chance to be on that flight as well as Sergey. We finished that part of the assembly up, and we're back in the factory. This is the secret Tupolev bomber factory inside of Moscow. We're looking at the module we're going to live in for the duration of our expedition. That module was up from Kazakhstan in middle of 2000. And now we have another hardware up in space that is habitable. And our crew is going to get ready to launch. Here we are in the Red Square. We follow a lot of the tradition of the Russian space program. This is Gagarin's gravesite on the Kremlin wall. Here we are down in Kazakhstan. The white shroud in the background is our capsule. It's going to be made into its booster. One of the real highlights of the time at the launch pad, this is a museum next to where the final assembly integration is done. We signed a lot of logs, but the coolest thing was right next door. We got a chance to look at this cottage. You can see it here in a second. Here it is. This is where Yuri Gagarin lived in 1961 before he was the first human to go into space. And Gagarin's bigger than Michael Jackson in North America. This is our booster. It's also called a Soyuz. It's a Soyuz booster. It comes out in a large rail car. 3 days before our launch. It goes out to the launch pad. It takes about an hour to get out there. Russians cranking up a big hydraulic jacks. And here we are getting ready to launch. This is October 2000. Everybody signs their name on the back of their crew door. We get a little freshwater wash down here. Ceremony. And here we are in our spacesuits, getting ready to launch. Yuri saluting the marshal that's in charge of the launch facility. Here we are in the base of the rocket. This is Russia. We have about 400 people right in the base of the rocket. This is 2 million pounds of stuff right there ready to go boom. And half the people are drinking, the other half is smoking. So we get in the elevator, we go up to the top, we get strapped into our couches, close the hatch, we're ready to go. About 10 o'clock in the morning, 31 October, lighting up. This is it's a series, it's clusters of liquid rocket motors.
3, 2, 1. Liftoff of the Soyuz rocket, beginning the first expedition to the International Space Station and setting the stage for permanent human presence in space.
Yeah, this thing's dying on something. We need to listen to it. So we're pulling about 3 feet inside the capsule here. Yuri in the center, Sergey on the far side out on the seat in the lower left. And we've blown off the aerodynamic shroud. And you see some rustling here. And then comes up nice. We're getting a signal that we have a good insertion. We have the cameras now. This is a highlight of the skateboard. Try to run a joke in Russia. Their face is going to get full because all the fluids coming up out of the lower body. It look like little pumpkins. We're actually in the same orbital plane as the station, but underneath it and far behind it. And every revolution we're going to catch up to getting closer to being under it. And the final day we're going to boost up a little bit and down a little bit. It takes 2 days living in the module. It's actually called the living module. It's about the size of a small SUV. And 3 lives, 3 spacesuits, not a whole lot to do. But we're making some pretty comfortable. And when you wanted to go to sleep, you fasten yourself to the bulkhead. And you want to put something up over your face or your eyes because you're going to see a sunrise 16 times a day. That can get disturbing to sleep. So here's what we're going to do. This is early Expedition 1 configuration station. We're maybe a mile away, and we've got a little radar helping us dock. We're going to fly right into that disk on the upper left side, right between the silver arrays, and you'll see the docking television here, right? This was a picture that was sent down to Moscow of our final approach and docking. We're going to smack in that cone at 12 o'clock, right? So you hear commands in Russian. That's cool talking about we have mechanical connection.
Let's look upon this as the real opening of the international space frontier, not just for a country, but for Russia, America, Europe, Japan, Canada, and all that would follow.
This was the first week in November, and it started a period that was very enjoyable for us because we were mechanical guys and we had our tools that we had to build everything. It was a lot of fun. I had a little impact drive, and perhaps drove the ground too easy because he would take anything apart and it was kind of up in the air whether we could actually get it back together. This is very comfortable. You can see computers in the background. And that was the command post for the ship. Here we go. You're sitting facing on the air conditioning. The first progress resupply vehicle coming up with about 4 tons of cargo. Here we had to fly the vehicle in the air. This is right here. If this radar comes over the images, I had to take over and do it by hand. It was not the normal procedure, but lots of good things inside, including something you might like oxygen. December, the first shuttle's coming up. This is Endeavour carrying the first of 4 large solar arrays. This is the bulk of our electric power. Counting sunlight and darkness and the orbital period, which is about 92 minutes, you have about 40% of that in darkness. This system, each set of wings generates 27 kilowatts of power. But really, its production is more than that because you got to stuff which you generate into batteries so you can handle the dark side of the orbit. So the output of these arrays is close to 40-45 kW by the time you're done. You have a cooling radiator that sits up on the top. You get this done with Any Navy guys in the audience? Any Air Force? I always like to pick on the Air Force guys because I tell them we're going to be doing that in space probably for the next 1,000 years. So just get used to it. So, in that one back, we saw pictures of what the station looked like. Our crew continued the assembly and outfit of all the components. Sergey fixing some broken pins on the wiring connector. A big part of our day was getting some exercise. We had a treadmill, a bicycle, and a little jungle gym thing. And this is very important because when you get back on the surface, whether it's the Earth or the Moon or Mars, you want to be functional when you get there. And we found that if you have fairly aggressive exercise protocols, the countermeasures work pretty well. So I think that problem, for the most part, is gone away. The highlight of every day was getting at the food. You know, our menu was half US and half Russian. And actually, I got to the point where I liked the Russian food better because it was more tasty. Sergey has a bag of Russian soup, and it was really good stuff. We had kind of a little crew conference at every meal, and they used this to kind of discuss how the day was going, what changes, what problems we had. It was a really good time to kind of face the crew activity during the workday. Sergey is spinning a bag of tea here, and kids would really like it because you can play with your food in orbit, and it's okay. And also, the human body is incredibly adaptable. And your stomach, after you get acclimatized to space, which takes a day or two, you really don't care what attitude January 2001, second shuttle came up and brought aboard the large U.S. research lab called SNAME. You see the shuttle's arm docking it, and you see in a second, two astronauts are going outside their space suits. You have to do walks on the outside to hook up the thermal radiators, the electrical power, the command and data lines, and some of the antenna stuff, so we can power up the module and get inside. It's a safe environment inside the module. And Bob Kirby, one of the two astronauts, opening a hatch. And I'm inside with a golf shirt on, Bob's outside. Complete vacuum, minus 200 degrees. This is what the lab looks Yes, you're basically. So now, cruise stream. Atlantis departing. We have our little departure ceremony. And all the crew's going to dive down that hatch. We're going to close both sides of the interface, evacuate it. The shuttle's going to undock. And all the shuttle crews can be back in Code Beach drinking martinis in about a day. And we're kind of in the middle of the winter with somewhat of an unknown when our expedition is going to be over. So we're going to be working on some repair procedure. We've got a voltmeter out in the kitchen table from the outlet. And that's the sleep stage in the background. The dots on the ground wanted to make sure that they were still alive month by month. I'm trying to find Mary's liver, and Sergey's saying it doesn't happen anymore. This is Sergey remembering his mass and oscillating spool. And every couple of days we take the trash out and we start it back to build. And we're going to do this when that cargo vessel detaches and deorbits. Everything's got to be tied down, or the motion control gets kind of haywire with its attitude control. This is March 2001 now. This is the shuttle Discovery coming up, the third shuttle to visit. They bring a large logistics module that was built in Italy called Leonardo. And this is how we moved really big things from the surface up into the station. And conversely, when we're done with an experiment, we send it back down. And so we're getting inside of Leonardo. And this is the size of the small school bus itself. But one of the interesting things, besides carrying all the stuff in there, you see it packed really to the gills with cargo. The replacement crew, the Expedition 2, that's going to swap out here.
Single-handedly extracting a rat from the infrared.
This rack weighs 800 pounds.
The first expedition crew is present and accounted for.
Change of command is
Change of command is an ancient naval tradition.
the
The passage of responsibility for mission, welfare of crew, and integrity of vessel from one individual to another.
Space Station Alpha
Has been commissioned in orbit.
The service module has
The service module has been activated.
the power element
The power element and laboratory module have been brought aboard.
a successful
A
resupply.
successful resupply mission with Discovery and her crew is complete.
Station is in normal
condition,
all systems functional.
all systems functional and ready to carry out operations.
We are on a
true spaceship now,
making our way above
any earthly boundary.
We are not
the first crew to board Alpha, or the last to depart.
but we have made
But we
Alpha.
have made Alpha come alive.
We gave her a name,
We gave her a name
substance,
and put substance
the ideas
to the ideas
that our crews can work
that our
together
crews can work together as
in
equals
countries,
and our countries as partners.
that we may proceed
That we may proceed with bolder and more enterprising voyages in space
benefit
and benefit from our differences
with a stronger
and with a stronger purpose
common
in our common goals.
We pass to your
We
care
pass to your care Alpha's law with the hope that many successful entries here are recorded,
explorations,
that explorations are prodigious
discoveries,
and discoveries wonders.
with the
May the goodwill, spirit, and sense of mission we have enjoyed on board endure.
sail her well.
Sail her well.
I am ready to give you
I am ready to be released.
And I relieve you.
And I leave.
First change of command in space, that's another thing we're going to get about the next 1,000 years. So we get on board Discovery and Untitled. And let's look at how much the station has grown since we were first aboard. And here's the Discovery in the middle of the night at Kennedy Space Center. It's touching down.
Main gear touchdown.
Kelly will be deploying
The drag chute at the moment. Discovery rolling out on runway 15 of the Kennedy Space Center, wrapping up a 5.3 million mile mission, bringing home the first residents of the International Space Station after 4.5 months in orbit.
We have about an hour to climb out of our suits, and the crew transfer us to a van. We go back to the quarters in Florida. And the next day, we fly back to Houston, where Anthony friends are the main people who has the ground operations and the program for the space station. Some of the traditions that NASA has, we used to have a big ceremony in Houston back in that's kind of caught on advanced now. So it's a hangar with 1,000 feet by all yelling and screaming, and the ceremony goes on for quite a while. Then we get a chance to get behind the scenes with people we haven't seen in some cases years. actually going to help things that are going back around the planet Earth. Here's here the space science. And I was trying to get my jaws to figure out if they're random variables. And that was our mission. Expeditions are going to have probably four main characteristics. One is the vehicles are going to be very, very big. Probably bigger than what you see here. This is almost 1 million pounds of stuff in orbit. It's 920,000 pounds. This is the size of a football field. It took almost 40 shuttle flights, carrying components up to build it. There were over 60 Soyuz flights and a number of other partner unmanned vehicles from Japan and the European Space Agency. So these projects are immensely big. I think if people go to Mars, they're going to be even bigger. When you are on your way to Mars, your communications are going to be very cumbersome, and this is something that we don't enjoy now that we've got to get used to. The station or the vehicles that go on these expeditions, they're going to be too expansive for one country to foot the bill. We're going to have a large international consortium to put this all together, and I think there are tremendous advantages to that. If it hadn't been for the participation of the Russians, their launch vehicles, their fuel for reboots, etc., we had at least one instance where the shuttle was grounded. We could not support what the station needed in the way of logistics, and the Russians stepped up. We would not be flying the space station today without that Russian partnership. This was a point that was really overlooked in the early 90s when people were kind of aghast that we would bring the Russians into the mix, but it's proved very, very efficient and productive. The last thing is that these vessels can't be checked out on orbit. So all the things are checked out on the ground. All the things that you work with, the thermal systems in particular, but many of the other subsystems, there's no way to really test these things end-to-end on the ground. So it's going to have to be done. It's going to have to be done in a regime where you can, if you have a part you need, you can, over a period of weeks or whatever, you get it and fix it. So assembling an Earth orbit with either robots or autonomous capability, or astronauts going on doing spacewalks, this is another character of these vessels that will go on these long expeditions. And so, logistics on Mars, if you didn't bring it, you're not going to have it. So there's going to be a lot of emphasis on the robustness in the platform itself, the ability to repair yourself, and I think it's going to rapidly get to a situation where, kind of like 3D printing, you're going to be able to make what you need but you don't have. And this is a great place for that technology. The last thing is, inasmuch as flying on the space station is different than being on an airplane, more like a ship, the whole aspect of who's in charge and what are they responsible for is something that the space station program has wrestled with. I was a Navy guy. I knew that our flight was not going to have continuous communication. We had comm outages that sometimes were 4 and 6 hours in duration. The ground's in the habit of preparing lots of commands to configure the vehicle, and when they have a comm outage with a shuttle, it's very brief, it comes back into what they call acquisition signal, and they will send 30, 50, 800 commands up to manage things on the spacecraft. And my point on the space station was, look, you guys on the ground have not seen this vehicle for 4 or 6 hours. How do you know that this thing that you're going to try and reconfigure is still in the right state for you to send that command without something bad happening? And I fought the Russians and the Americans tooth and nail that the crew had to be more involved with these decisions about when things on board would be changed,
what's to be changed, and how is it going to be observed. And so to that end, we did something that I would call on a ship an 8 o'clock report. I'm sure anybody that's sailed on a ship has seen something like this. And it's a statement every day of where you are in terms of your altitude, how much fuel you've got, your capability to maneuver or to reboost, any threats that are out there as far as debris headed your way, your consumables, your electrical power output. It's just like a captain on a ship kind of seeing every morning before he's got to work with that thing. NASA's been away with us for about 10 years, and I was just in Houston 3 weeks ago, and they have since brought it back. So somebody down there had an attack of reason, and they have this back in the program now. But this is the kind of stuff, it's shipboard stuff, and this is why we will need it in the future. So we talked about a lot of this, large vehicles. Another thing that's going to happen is large vehicles and surface explorations are going to need lots and lots of electric power. More than we're going to be able to have with solar or chemical sources. So I think, Bill Shepard thinks we have to do nuclear power, and the sooner the better. We talked about assembly and then testing redundant systems and fleets. So I leave you with all this tonight that this is a roadmap for what space exploration is probably going to look like in the future. The only question I would have is, when are we going to buckle down and get it done? And I don't know the answer to that question. So that's the conclusion of my technical presentation, but I've been advised that we have to have a sufficient technical content in the presentation tonight, so I need a lot of good questions, particularly from the young audience. Who shall be first? Mike? Go ahead.
My name is Josh Gavin from the Merchant Marine Academy. So you mentioned the technical challenges in the ISS and what it will take for us to get to Mars. I recently read Captain Scott Kelly's book Endurance, about a year in space. He mentioned some of the things that he thought would be difficult pertaining to CO2 and waste disposal systems and reclaiming water. So for the nuclear side, what do you think the challenges would be for implementing that technology in the ISS or necessarily for getting to Mars? What would you perceive to be the issues with that tech if that were to be implemented?
Well, one of the big ones would be the radiation, but I think we could develop shielding and a configuration of spacecraft where the nuclear core, the power element, is relatively far from the spacecraft. It may even be out there a long way on a tether, and you're just sucking electricity back on that wire. These are lots of different ideas, and then you only have to shield a very small, solid angle to keep the radiation off the crew. The advantage to that would be that we're limited right now in the way we can move around in the solar system because it takes a lot of energy to do it. And so when we plan trajectories to the moon and to the other planets, we put spacecraft on these elliptical transfers that are designed to require the absolute minimum amount of extra velocity, delta V. And so not only are we restricted in how much energy and power we have to make that transfer, it's also the case that many times in the years of the solar system, the alignment of the planets is better than others to do. So we would have particular years trying to go to Mars that happen once every 6 or 7 years. It would be really optimum if we try and go on off here. We could use twice as much energy to get there. Nuclear power takes away a lot of these restrictions, and also it allows us to build rocket engines with considerably more energy density than we have right now with these other chemical and solar systems. So the challenge for a nuclear propulsion scheme is, even though you've got a boatload of energy, you have enough, can you make power with it in terms of thrust? And there are several technologies that are working right now to use various fluids that need a lot of electric power, more than we can provide in conventional energy storage systems. And so nuclear power is a way to do that. One of the engines that's being worked on in Houston right now is being developed by a former astronaut, and it's a system that promises to be able to put humans on a Mars transfer orbit or passage that would, instead of taking 270 days to get to a Martian orbit, it's more like 60. And I think that's where we need to be going. So all these problems that Scott's talking about in terms of consumables and regeneration of environments, yes, there are important problems and we need to solve those too. But I think being able to go vast distances quickly is probably our biggest technical challenge. When we get to Mars, we're going to need tens of megawatts of power. We're not going to get into solar systems. Mike, go ahead.
I was curious about the safety used while designing vessels for space travel. I know when I heard about the safety of designing everything with remote stuff, and how small they were,
yeah, it's a great question. The general kind of kitchen number people use is 1.4, but it depends on the system because NASA has had a design philosophy where everything is triply redundant, which means that generally you can have one failure in a component and you don't lose any mission capability and you don't endanger the crew. You can lose two that are supporting the same function, and your mission might go away, but you're not going to destroy the vehicle or lose the crew. And so they have three levels of redundancy for everything: switches, wiring, relays, computers, auxiliary power units, yada yada yada. And it begs the question: is that really the most robust way to do things? One of the big advantages of working with the Russians is you get to see, you get into the mind of the Russian designer. How do they build their spacecraft? They don't do that. They will have one system that's relatively whiz-bang that might be computer controlled, but then they'll have a dirt simple agricultural industrial strength backup system that no matter what this stupid computer does, this other system, you can switch the computer off and get the job done with this probably labor-intensive but mechanical way to do the same thing. I personally think that's a tremendous design lesson that we need to look at hard because there is a limit to the level of complexity that we can build these systems and still be able to operate and maintain them for essentially what will be decades. And so it's kind of a question, what culture do you really want to chase when you build these new things? One note that you could amaze your friends. We had a service module that we lived in. It was built in Russia, and it's welded aluminum. It's a skin. And it's relatively soft alloy. It's 2 millimeters thick, and of course it has armor shielding on the outside of it for impacts and meteorites and things. But if you want to get a sense for what that is, take an aluminum soda can and rip it open or cut it in half and look at the skin of that soda can in relation to the diameter of the can. That can, the skin, relatively speaking, geometric scaling like we talked about the other night, that can is 3 times thicker than the hull of the module we lived in. So you've got 2 millimeters between you, and the rest of eternity. It's something you think about at night. Other questions? Well, we're going to have some more questions. Sir?
An obvious question. Were you fluent in Russian before you went on it and your counterpart when you flew in English?
Actually, my two Russian cosmonauts, one was a completely native English speaker, the other guy was fluent. I got fluent in Russian as long as the conversation. It took me 3 or 4 years of study in Russia to do this. And as long as the conversation was about a vocabulary I was familiar with, that I was okay. But one of the things that happened to me early in the flight, right when we got on board the service module, we opened the hatch on it. The next day we had a press conference with Europe, and so we're floating around in this module looking at a TV camera, and we're getting ready to be broadcast live to Moscow to a room full of reporters. These are reporters off the street, and they're really no different than the media in the U.S. They're getting ready to ask you any crazy question they can think of, whether it has to do with space or not. They can see you, they can hear you. You can't see them, you can't hear them very well, and they're going to ask you these wild questions live in Russian, and you better have a good answer. I'll tell you, that was stress. But we got to. Another question, sir.
One of the things that fascinates me is that you never said anything about that. How do you handle waste?
Well, the supply module that you saw come up where we open the hatch, we have trash that we throw in there, and we have both. Now they reprocess the urine and extract the water, but at the time they were filling up small aluminum containers with human solid liquid waste from the Russian toilet, and they go into that module, and it gets deorbited and it burns up in the upper atmosphere. And actually, it's a pretty good system. Again, back to design philosophy, there had been a desire from NASA to take the space shuttle toilet and redesign it for space station. And we, in the program, said, now we want to save money, let's just use the Russian one, because it works. And so I went to flying space. It turns out later, people at NASA were developing the NASA space toilet. This thing had 12 or 15 computers on it. I kid you not. It cost many tens of millions of dollars, and the damn thing never worked. And the Russian toilet had almost no electronics, no computer on it. It worked like a charm. It was relatively sanitary. You could take it apart, replace the bad parts, put it back online. You could do it on orbit in zero gravity in 30 minutes. So, now, which toilet would you rather take to Mars? It's an easy question. This is the kind of stuff that part of my frustration with the way our space efforts are being managed was we had this tremendous opportunity by exposure to these other countries, and not just Russia. The Canadians and the Japanese are very smart, as are all the Europeans. We need to harvest the best of what these people do, and that's the real strength of a program like this. We are not capturing that. That's what frustrates me. Question over to
Great to hear your speech, sir. One of the things I wanted to ask you, one of the hardest parts about sampling is being away from home and not being able to communicate with your loved ones and everyone else back home while you're at sea. Being out in space, how do you handle any situation back home? How was it for you, talking to your loved ones and handling things?
Great question, and once we got the communications a little more robust, I could talk to my wife just about any day on a routine basis, and if it was something important, she could go to mission control or call mission control, and then she could patch into the station. So there's something really important I could discuss with her. We got to the point where we had that digital video. We could, basically Skype toward the last half of our mission. That was great. But again, this only works when you're close to the Earth. When you're 20 minutes away on a Mars mission, it's going to be a different deal. I just finished a summit in Houston where we talked about some of the human factors for these long explorations. And that was one of the biggest ones. You know, what happens when you have a spouse, man or woman, who is going to disappear for 3 to 4 years, and you're not going to get all that close to what kind of family relationship is that going to be? And so I was telling the group assembled, I did a fair amount of work in my Navy days with my SEAL buddies. And one of the stories that I really like that's relevant is the SEAL teams have chaplains now. Great people, they're there to help. And so initially the chaplain came in and they didn't really kind of know how we're going to fit in with this team of men and women. But so somebody would have marital problems and the chaplain would come in and say, son, let's have a cup of coffee. Let's sit down, let's close the door, relax, get this off your chest, tell me what's going on. And that worked only for a while, but it got to the point where so many people were filing for divorce. To get to the chaplain's office, you had to pass kind of an administrative guy at the front of this hallway. The chaplain's office was at the end. And the chaplain would come out, and each box was labeled with the name of the state on it. And in the box was the paperwork you had to file for divorce in that state. And he came out and said, divorce, yeah, okay, here's Tennessee, your box is over there. Maybe it's a production line. And I think we need to think about stuff like that with astronauts because they're going to be in a similar situation. It's going to be a rare family that puts up with that without some kind of heartburn. We're not ready for it. Other question?
George, I have 2 questions. The first is whether you had any machine shop capabilities to fabricate it. And the second is what you talk about.
The breeze easier. I'll talk about the machine shop in a second. One of the parameters for the design of the space station was going to be how to get protected against debris. And the studies that we relied on at the time put debris in 3 categories. We have radars that we use for missile warning and other things that look at the horizon, and they can detect relatively small objects as they break the Earth limb, and they can say, okay, that's what that is. We track them all the time. And some of them are nose cones, pieces of boosters, meteors, or whatever, and it's just up there flying around. And we track it, we can say, okay, they run the orbital trajectory ahead of time, and they say, is that going to be a problem for the space station? If it is, we maneuver the station. We usually know at least a week in advance that we're going to be close. And so the big stuff we avoid, the big stuff being about the size of maybe a large melon in terms of just something to look. And it has a lot to do with radar cross-section, which varies a lot depending on the material of the shape. The small stuff is down around smaller than golf balls, like large ball bearings, down to dust from paint powder off of boosters, which a lot of that is space. The small stuff, we could build armor without too much of a weight carry and put that on the modules and say, okay, we can handle the small ball bearings, we're okay with that. Might dent the hull, but we're not going to lose the compartment. And so the stuff you worry about is the stuff that's bigger than ball bearings and smaller than melons, which you can't see, but if you hit one, it's going to be a bad day. So the analysis and the mathematicians got together and they said, well, we should design a space station so that the probability that you're going to have a strike from a particle, an element that's in that size range, it's a 1 in 500 year event, and that's what we designed to. And walking down the street and getting struck by lightning is a lot more probable. The issue is the Chinese, about 4 years ago, had an anti-ballistic missile test. They smoked one of their own satellites in low Earth orbit. We asked them not to do it. We have international treaties that basically prohibit signatories from doing stuff like this. They blew it up. They increased the debris density in this one part of the low orbit space regime by 30% in one afternoon. It was a real bad move. So people are debating now if there is a point where there's enough stuff flying in space, enough things to run into like satellites and spacecraft, that when you start hitting them and breaking them up, is there a drop-off point where it's going to be a chain reaction that just speeds itself? And there are some pretty good theories that say that may happen. Right now, NASA does not buy into that, but it's something to be considered. Machining in space. I was a big proponent of being able to repair and fix whatever we thought we could handle on orbit. We did several repairs on the space station that we were told from the ground, things that were busted. They would say, hey guys, we know it's not working, just leave it. And we said, okay, when are we going to fix it? And they said, yeah, we got the plan to fix it. We're going to send up a new component, but it's going to get there 6 months after you guys leave. And we I held my Russian guy and said, we're not buying that. And so we had at least 3 things that we fixed that the ground said could not be fixed. With some wiring, some soldering, a little bit of fabrication with the files and the sheet metal. But we did it, and the ground would notice that this thing that was busted suddenly came up and they were getting telemetry from it, and they would say, hey, we see the CDRS element is working now. What's going on? And we said, well, we took it apart last night and tore into it, and we figured out what was wrong, but we jumped it and we turned it on and it's running. And they said, well, where'd you get the procedures on how to do that? And I said, no, we just made it. And they said, we could go back in and break it again. They said, no, just let it run. So, but I think fabrication in space is a big deal. We made the galley table that you saw in the video. That was an unauthorized stealth project. It was made from scrap aluminum containers and parts from the cargo craft, because we came up and we were expecting our galley table to be there, and we called down to the ground and we said, hey guys, where'd you stash the galley table? And we said, well, we couldn't manifest it because we had too much other stuff and it's going to come up. We said, okay, when? They said 6 months after you guys did. So we had a stealth project. We didn't tell anybody. We actually did we did metal sawing on orbit. We had drilling, tapping, threading, filing, whatever. And what we did was we controlled the solid waste with shaving cream, a little lotion. We put a glob of shaving cream on where we're cutting, and that captured all the metal particles, because the ground was crazy that these little metal particles were going to get into everything and cause a bad, lots of bad things could happen. And we just wiped it up and threw it in a trash bag and we're done. And it turned out to work really well. I don't know if they bought into that officially now, but I know a lot of other astronauts have done it. So I really think this manufacturing in space is going to be a big deal. And I would like to see the space program pioneer this, not only for how nobody's going to go in space and be really good at doing that unless they've done on the ground. So I think there should be a very aggressive program at NASA now to do this in situ manufacturing, and it's something I'm trying to push real hard. It's not getting anywhere, but if any of you academics want to work on manufacturing in space, let me know. I'll see what I can do to help. Other questions? Sir?
Hi, I'm Sean Healy, a freshman from Webb Institute. I'm wondering how long it took you to acclimate into outer space. About how long until you felt you were actually comfortable?
For me, it was about a day and a half where I felt like there was nothing I was sensing. bothered me. I could eat whatever I wanted to eat. Orienting myself didn't sting me or anything like that. I felt pretty good on my first space flight from managing the cutoff and we're weightless because I thought it felt a lot like scuba diving and there wasn't a lot of water around, but your sensation of how you could move in that environment was very similar. But people are different and human response varies a lot. There have been people who have thrown up for 4 or 5 days before they kind of got over it, but that's not the norm. Most people are fairly well adapted in a day or two. So,
you've talked a lot about the need for cooperation between nations in space programs. What are your thoughts on the current privatization of space exploration?
Well, I think the initiatives are good. We do need lots of people trying to put their technology into space. The only problem, well, I've got two problems with commercial space. One is the way it's being managed right now, it's not really a commercial market. These companies are selling logistics and eventually crew support to the U.S. government. And it's only one customer. It's not a market. So can that be broadened somehow to space tourism, other space stations? I don't know. So we're not really into a commercial model yet for that kind of capability. The second thing is we have a large number of wealthy people and particularly Hollywood celebrities who want to be able to go to the bar and say, hey, I just got back from my space flight. What did you do last weekend? And I think that space tourism is okay, but I wonder if all these people realize that getting up into space and getting back, any way you cut it, is still a very risky thing to do. There's no way, in my mind, in the near future, we're going to make that really safe. The risks are going to be manageable, but anybody that goes to the launch pad and says, piece of cake, they think they're fooling themselves. And I think that's another aspect of the commercial enterprise that is not really well described. Way in the back.
I know you mentioned the need to continue the slow march into space despite the substantial cost monetarily. Is there any tangible benefit that you could, propose to policymakers other than the sake of exploration?
Well, I think the best response to that is there are so many things that come out of the technologies and engineering approaches that we use to do things in space. It's very hard to quantify directly what the benefit is, but I'll give you some thoughts on that. The Apollo program, I really commend anybody, a show on Discovery Channel called Blue Machines. It was done 5 or so years ago. It's a 5-part series, fantastic documentary on the rockets, spacecraft, and particularly navigation and the computers. And one of the first contract that was let for the Apollo program, and this was in probably 1962, was to MIT, to the Draper Instrumentation Lab, and their job was to design and build the navigation scheme that was going to get the Apollo spacecraft to the moon and back. And at the time, transistors were around, but this was very much transistor to transistor logic, TTL. I'm not sure kids even know what that is anymore in school. Vacuum tubes were just passé, and IBM had just made the first transistor mainframe computer. That's the era that we're in. And then in the early 60s, Intel and others started making integrated circuits. So at one point in the mid-60s, the U.S. space program was buying and using 60% of all the integrated circuits in the world. And there was a particular demand, but to make a computer that was small enough and efficient enough to fit in the design budget they had for the Apollo spacecraft. That's where they had to go, and they paid a lot of money for it. But that, when you look at your cell phone or your GPS in your car, whatever, I mean, that's where that stuff comes from. And I think when we do it again, to put humans and bases on the moon and fly people to Mars, we'll see some more stuff. I think there may be a day when we figure out how to provide extensive nuclear power with a minimum amount of environmental issues. And I don't know how we're going to get there, but to keep doing very aggressive research on how to make that work. And just that would change everything. So I can't give you a direct monetary answer to what the benefit is, but having seen it up close, I know it's there. Maybe one more question? Okay, we got two more questions. How about the lady back?
Earlier you talked about nuclear power for the future expedition. Nuclear power on that naval mission is really helping us fully for a cold loop. I was wondering what the thought process was for cooling.
You have to radiate to space, and that's one of the big design problems is how do you have a radiative system that's efficient enough to throw off all that heat? To make 50 megawatts, you got to get rid of a bunch of megawatts of heat. So there has been some research in direct electrical conversion of nuclear power without all these crazy thermal cycles, and that may not really do it.
With all the scientific experiments that we've done, I guess, over the years, what were the most significant breakthroughs that you can talk about?
Yeah, I'm not a hugely knowledgeable science guy because I like the engineering part of it. But let me give you a couple of examples. One of the things that we did on the space shuttle was we flew about a dozen missions where we have a small drawer-sized experiment that looked at crystals that form have solutions that have proteins in them, and if you dry them very carefully in zero gravity, they form a large crystal. And the utility of this is you bring these crystals back and you shoot X-rays at them, and because of the way the X-rays bounce off the surfaces of the crystal, even though the individual proteins are very small, because it's a crystal, its shape is repeated over and over and over again, and the X-ray image gives you an idea of the arrangement of the proteins and what the proteins look like. And this is used for drug discovery, and when I flew my first flight where we had one of these protein crystal growth experiments, there were about 160 some proteins that had been analyzed in laboratories, and people could say what the structure of the protein is. And why would you care about protein? Well, proteins are everything about us. It's how tall we're going to be, what color our hair is, how our kids look like, maybe even what diseases we're going to get. That's all tied up in the protein structure of humans. And so understanding what these things are is pretty important. So 160 were known, 50 some crystals that they knew about were crystals they had flown in space. And that was done over a period of years on the space shuttle on more than a dozen flights. We have laboratory racks on the space station now where the whole rack is not only protein crystal growth, but the X-ray analysis. We can do the same amount of work that was done over nearly a decade on the shuttle. We can do that on the station in probably 2 afternoons. That's the difference. It's one of the big life science, biomedical research things that's going on. There's another big experiment on the space station called the alpha mass spectrometer. And this is a rather crazy experiment. I don't claim to understand it, but this is about showing through data the existence of dark matter. And it uses presence in space, the Earth as a basically a blocking filter, and over a long period of time you can collect data that shows kind of what dark matter is. And you could say dark matter, dark matter here. Physicists, and I'm not a physicist either, but the current thinking is 70% of what's out there in the universe that's causing the universe to expand faster and faster and faster has to be dark matter. We can't see it, but we're pretty sure it's there. I mean, these are the ways that we start to better understand the fundamental structure of the universe. And that's what this is all about. Okay. I think we're done, man.
Okay, well, that's great. I wanted to make that I thought, just during this talk, I found it very interesting, and bringing it back from space back to the maritime industry. A couple of the points that you made I thought were really interesting. One of the things that we talked about was how to rely on lifeboats in space. Especially for the long distance missions. And one of the things you said was, well, maybe we'll be going out in a group of ships. The maritime industry has been struggling with this very topic for 100 years, 150 years. And I found it very interesting because the original idea was, well, maybe we don't need enough lifeboats on a ship because there will always be ships out there. There will always be someone who can rescue us. I'm thinking Titanic. These are things that maybe both the maritime industry and the space industry need to talk together. At the same time, more recently within the International Maritime Organization, is a concept that we're calling safe return to port, thinking that the ship is always safer than a lifeboat. So if we can avoid the need of a lifeboat and use the ship as that lifeboat, maybe that's another avenue that's worth discussion between the two. And the other thing I thought was very interesting when you were talking about when you dispose of garbage and it goes back in the capsule and it has to be tied down because you don't want the motions of the garbage to affect the inertial have inertial effects on the capsule. To me, that I took a lot of that from I thought of ship stability.
Yeah, it's free surface.
Well, it's free surface. Anyone who's ever been involved in climbing, you want to tie down a roll. You want to eliminate any hanging weights. And I just thought that was really, really interesting, how the two of them are related. Now, I know that in previous discussions we had talked about also different research that had been done by the maritime industry, organizations such as SNAME and IMarEST that have looked at aeronautics, even links to NASA. I want to thank you. You highlighted a couple of papers, very, very old papers, in fact, from the very start of the aeronautic industry. Papers from 1911, even 1924. If anyone's interested in learning more about those, we do have a couple of copies of them up here. But just for the slides now, if I remember correctly. This being one of them, some applications of the principles of naval architectures to aeronautics. That was actually from the SNAME transaction in 1911. I found a couple of others since. We have a couple of copies of those papers and a couple of reference lists. If anyone's interested in learning more, please feel free to contact me and I'll be able to help you. Even to this day, there are links between NASA and the maritime industry. And one of the things I just wanted to point out was even the Johnson Space Center. Right now, there's an organization within there that train not only within the neutral buoyancy tank. Most of that tank is used for the training of astronauts. I myself was down there a few years ago for a basic offshore survival course, and we were actually practicing helicopter dumps and helicopter evacuations in the very same tank. So even today, to me, it was fascinating to be able to say, I'm in the same tank as these astronauts. It was just a wonderful thing to be able to see, and it's good to see that the industry is still working together. So once again, thank you, Bill, very much. We can have a round of applause, please. The first one we have here is just a certificate of appreciation from the Institute of Marine Engineering, Science and Technology, Eastern USA branch, thanking him for the time for the presentation. And secondly, this isn't something that we normally do, but because of the tremendous efforts that you've made to help us and just the high-profile presentation that you've given us on behalf of the IMarEST in London, we would like to issue an honorary membership of the Institute. So thank you very much for that.
I'm going to need a picture.